slides briefly. We have a few slides to look at. So here was our step 11, there's our step 13. So now we're going to switch to dynamic spontaneous rupture. And so we're not going to do things in a big 3D domain. We're going to look at a bar that's allowed to deform and shear. It's going to be an 8-kilometer long bar. And we're going to look at it in 2D. So we're going to use here's the examples bar shear wave quad 4, and in this particular example, suite of examples, we can look at spontaneous rupture with static friction. There's a spontaneous rupture that's spelled wrong. That should be weakening. We'll fix that in the slides. Spontaneous rupture, rate and state aging, and so in this directory, we both have kinematic and spontaneous rupture. And so all the spontaneous rupture parameters are in this file. And then there's a separate file for each of the different friction models. So there's a static one, there's a slip weakening one, and a rate and state aging one. And let's see. So here's what our sort of simple diagram of the problem looks like. We have a fault in the middle of our bar. It runs all the way through. Our bar is 2 cells by 2 cells by, I believe, 400 cells. At the ends, we have absorbing boundaries. So we're going to generate it. We're going to cause fault slip here in the middle by prescribing tractions on the fault that are greater than the failure threshold. We're going to get shear waves propagating down the bar. They'll be absorbed by the absorbing boundaries. And we're restricting all of the x degrees of freedom to be 0. So we're only allowing the bar to deform in shear. Our applied tractions are going to be as a function of time. We're going to have an initial value of 75 megapascals, and then that value is slowly going to rise up to 100 megapascals over a duration of 1 second. And so our faults will fail at a value below 100 megapascals, and so we're going to generate slip. Then when the shear wave hits the edge of the bar, it's going to hit the absorbing boundary, and we'll eventually go to a steady state solution of the 2 sides of the bar slipping past each other at a steady state velocity where the deformation within the bar is going to balance this 100 megapascals. So our 100 megapascals, part of that's going to be going into friction, and then part of it will be going into the deformation of the bar. And so you can actually, for static friction and slip weakening, we can analytically solve for what that sliding velocity will be. And so that's it for the slides. Let's go to stop sharing. Let's go to the directory. And so let's bring up the terminal window. Let's first look at the .cfg files. So this is going to be our first. So an example, bar shear wave 2 quad 4. And so first I'll bring up, these are all dynamic problems. So first let's look at the pilot app file. So I've turned on a few more journal debugging to show the progress. We're going to use a qubit mesh. It's generated in very much the same way as our other qubit meshes. We just took a block, sliced it in half. Now we're changing the formulation from an implicit time stepping to explicit time stepping. We didn't go over this. In all of our previous problems, we've solved an elastic problem and then marched forward using a perturbation, allowing inelastic behavior if it was present. In this case, we're not going to do this elastic pre-step. We just jump right in and start computing. We're now also switching from the default non-dimensionalization parameters to set it for quasi-static behavior, we're going to select the normalizer that is set up to be more consistent with dynamic problems. So instead of a time scale and a length scale, and I believe it is a pressure scale, we're going to have a shear wave speed, a minimum frequency, and a density scale. And we're going to use the defaults except for the shear wave speed. The shear wave in our bar is 1 kilometer per second. So we're going to set our normalization for the shear wave speed equal to that 1 kilometer per second. Boundary conditions are going to be on, we're going to have absorbing boundaries on the two ends. And then in order to constrain all of the extra degrees of freedom, we created a node set that was all of the nodes except the faults. We have a fault interface. We have a single elastic material. We're going to run for a total of 12 seconds, a time step of 0.05 seconds. Bulk constitutive model in our 2D is elastic plane strain. Our node set from qubit for our material is 1. We have material properties in matprops.spatialdb. We're going to use Fiat Lagrange. We're setting our cell dimension equal to 2 because we're using quads. We're going to set the quadrature order to 2. So that we have 4 points. Our absorbing dampers, so instead of using the Dirichlet boundary conditions, now we're setting the boundary conditions to being the absorbing dampers or absorbing boundaries on the ends. And so in order to set the dampers appropriately for the material, we have to give the boundary condition the information about our physical properties. And so we just tell it that we're to go look up in the spatial database. For absorbing dampers, we need a quadrature. So here we use a cell dimension of 1. Again, a quadrature order. We're going to be specified explicitly 2. Same thing on the negative X space. Same material properties, same quadrature scheme. To simply pin all of the extra degrees of freedom, we use the zero displacement boundary condition. That's the default for the Dirichlet boundary condition. The zero displacement database. All we have to say is we want to pin the X degree of freedom, give the label of the node set from qubit. Our material, very simple. This is for the faults. Fault ID of 100, and this is for. So in this case, this is our pilot app file that is working for both kinematic and dynamic or spontaneous ruptures. And so we don't even specify the type of fault, but we do specify that it's going to have a material ID of 100, node set of fault from qubit, and use this quadrature scheme. Notice for our PETSI parameters, for explicit time stepping, we don't use a PETSI solver, so there's no PETSI solver settings. And in our output, we're going to use I believe it's UTK output, which is the default. So in this case, we're just going to specify the displacements and velocities for the whole domain, give me every other time step. For the state variables, skip 19 time steps. And so let's look at spontaneous rup.cfg. And so spontaneous rupture, these are common to all of our spontaneous rupture simulations. So here we're going to set the fault to a fault cohesive dynamic or spontaneous rupture. We're going to use the same initial perturbations in the traction. So we're going to prescribe 75 megapascals of right lateral slip. Remember, positive is left lateral, so we give minus 75 megapascals for our shear traction. Less than 0 is compression, so we do minus 120 megapascals of compression. The amplitude of our traction perturbation is 25 megapascals. So remember, we're going from 75 to 100, so 75 minus 25 is minus 100. No change in the normal traction. We're going to start that traction perturbation at a time of 0. Our traction time history is given in a time history file. It's just a list of values and sort of a normalized amplitude as a function of time in the second column. We'll look at that in a minute. For our fault cohesive dynamic output, we want to output our initial traction value, and then on the fault surface, we're going to do slip rate, and traction. And so let's look at our static friction. So that's in another .cfg file. So static friction, here's our static friction parameters. Essentially just we're specifying our parameters of 0.6 for our friction coefficient, 0 cohesion, and then the only other parameters specific to static friction are our output file names. And we're going to use BTK output. So any questions about setting up a dynamic problem? So implicit time stepping is for when we have no inertial terms, so we're ignoring the mass matrix. It's for slow deformation. Explicit time stepping is when you want to include the inertial terms, so the effects of mass. And so implicit time stepping is for quasi-static problems where the deformation is occurring very slowly. The deformation propagates across the domain instantaneously. In a dynamic simulation, the deformation propagates as a result of the seismic waves. So the seismic waves transfer the deformation, and so it spreads out no faster than the P wave speed. In this case, in our shear bar, it's going to spread out at the shear wave speed because we're limiting the deformation to just shear. Any other questions? Okay, let's run this problem. So I need to get to the right directory. So here's my directory. I've got a bunch of spatial DB files. Let's look at, well, first let's just, the material properties. So my density here is 2500, shear speed of 1 kilometer per second, P wave speed of 1732. And then the other one was my traction change time history. So this is what a time history file looks like. This is my user-defined time history, so I can be arbitrary. I have 102 points in my time history. The units are seconds. So the first column is my timestamp. The second column is my normalized amplitude. So as I go down here, notice that I used sort of from 0 to 1. I used a time step of 0.01 seconds. And then down here, I went from 1 second to 15 seconds. So my time history file did not need to use a uniform time step or time sampling. Pilot is smart enough to go in and do linear interpolation. And so because I had sort of a smooth onset over 1 second, I did a fine sampling of that smooth onset. But once I reached my sort of that steady state value of 1, I knew there was no reason to have additional points in there in my time history file. So I can use uneven sampling of points, and Pilot will just interpolate. And I used a normalized amplitude here from 0 to 1. I could have done 0 from 2, but then that gets multiplied by whatever value I had for my amplitude internally in those settings. And so it makes much more sense to use a normalized amplitude in my time history file of 0 to 1. So I just control the amplitude within my .cfg file. So let's run. So I go spontaneous.cfg, spontaneous static friction. And I'm just going to let it come here to the, and so you'll see we're flying through time. And so we went through 12 seconds. Using explicit time stepping, I need to share my screen properly here in ParaView. Now we're back to ParaView. We're in the wrong directory, so I need to bring out our old stuff. Load up our ScheduleWave Quad 4 output. Let's load up our bar. Let's get which, there we go. Let's exaggerate things by a factor of, I think, 10. And I should add that, you know, that when we're looking at the magnitude of our stresses, we're using 100 megapascals for compression. So that's sort of, you know, down. Those are realistic stresses for something, you know, down several kilometers deep in the earth. And this little itty bitty bar, 100 megapascals, and talking about tens of megapascals of stress changes, they're going to cause some pretty fast slips and some pretty large slips. Both fast slip as well as a large amount of slip. So that's why our scale factor, we have an 8-kilometer long bar. It's 200 meters thick. And so we're going to do a scale by a factor of 10 on the deformation. And I'm going to play it here. So here's our shear wave propagating down the bar. So we've caused a bar to deform. We applied, and you'll notice that here, in contrast to a quasi-static problem where we would have the ends deforming immediately, the ends don't know that the fault is slipping yet. It has to take the shear wave. The shear wave is transmitting the information that deformation is occurring. And so it's going to, with static friction, it's just going to go to the static value, and then our bar just slides along happily. Our dislocation grows, even because we're assuming sort of infinitesimal strains and our geometry doesn't changing. You know, we've actually lost contact along our sliding surface, but Pilot doesn't know that. It assumes that the two sides are still in contact. So if I do a factor, even if I do a factor of 1, you'll see that things are losing contact. But Pilot still thinks everything is in contact. So it's not meant for the really large deformation. It's meant for small strains. But you can do these neat things like where we have the two bars, especially when they exaggerate it. I'll see how well this plays. This might not. It doesn't show up. You just see the end result. So that is static friction. You notice it just sort of smoothly migrated down the end of the fault. We don't see reflections bouncing back and forth due to our absorbing boundaries. Now I'm sort of replaying in reverse time. I should have colored my, so here's my velocities. You'll notice that my velocities, they're not exactly the same uniform throughout the bar. There is a little bit of stuff coming back from the boundaries. And there's also a little bit of chatter right at the fault. And so there you can see that at the ends, essentially I have 0 velocity, but then I'm up there at 12 meters per second. Right there is the fault slipping, so that's what those large stress changes cause large velocities. And then we settle down to a steady state value of about, I believe it's 11.5 at the very end, 11.1, 11.3 for a steady state value of the velocity. Any questions?
Lucia had one about does quad order equal 2 mean there are more points to represent one cell?
Yes, so there's more. So in order, with the quad cell, in order to get reasonable integration of the mass matrix, I wanted 2 by 2 quad. Let's see, that's a good point. What, did I use 2 by 2 or is it more than 2 by 2? So let's look and see. So let's go back to the terminal. I don't think I'm writing it has to see explicit. So Fiat Lagrange is 1, so we should have it in, I didn't, so I need to run it again. Let's capture the log file. And you can look at the top of the log file and see what our quadrature looked like. Okay, there we go. So yes, so with quad order 2, it's doing 2 by 2 quadrature. I think that is the default. So I didn't change it from the default. Let's we can play around. We can change it to quad order 3. And there you see in my quadrature points, looks like I have 3 by 3 by, sorry, 3 by 3 quadrature. Yeah, 9 points. So so I have minus 0.77, then I essentially have 0 plus 0.77, and then I have that in each direction. So 3 by 3 quadrature for 9 points. And so that increases the amount of storage, but my basis functions are still just linear basis functions. I didn't change the basis functions. And so 2 by 2 pretty much gives me very little error in my integration. So going to 3 by 3 isn't paying off. If I was to use a higher order basis functions, then I'm going to need more quadrature points within my cell. I need to change this back to 2. Any other questions?
Okay.
So let's do rate and state. So I'll just bring up spontaneous rate state. So here the only difference from our previous case was, remember our pilot app file sets all of the dynamic simulation information. Our spontaneous rup.cfg did all of our initial traction boundary conditions and so forth. And so the only thing, as we vary the fault constituent model, is we're changing the output file names and we're changing the fault constituent model. And so here we're changing to rate and state friction. Here's our rate and state friction parameters. This time our coefficient of friction is going to be 0.6. Our reference slip rate is 1 times 10 to the minus 6. We're going to use this critical slip distance. That's the L or D sub C, depending on which book you want to look at, of 0.02, A of 0.008, B of 0.012, cohesion of 0. And our initial state variable is 1.6 times 10 to the 9th. That gives us a reasonable starting value. Then we also have our output going to VTK. let's run pilot spontaneous rupt.cft spontaneous rupt underscore rate state. Again, no nonlinear solver, we can just crunch through with explicit time stepping. And so let's look at this in pair view. I'm going to keep my static friction on there. Let's put static friction in wireframe, and we'll load up a rate and state. So there's rate and state. We need to deform it. Let's see, I was warping by vector by a factor of 10, and let's delete this. Then what I'm going to do is I'm going to show you how you can simultaneously apply a filter to two things. So I click on static friction. I'm going to do on my Mac here, I'm going to do a shift, the Apple click on rate state. Oh, and it's not letting me apply. I can look at both displacements. It's not letting me apply my warp by vector.
Do you have to group the data sets first?
Oh, yes. Thank you, Charles. So I'm going to go up here, and this icon here, the circle with all the little stuff inside, I'm going to group my data sets. So now you can see I have a group data sets 1. I can come down here. I need to apply. So now on my group data sets 1, I can warp them both simultaneously with the same scale factor. And I guess the question is, they're both going to end up being displayed. I can't change the colors separately, can I?
I don't know.
I don't think I can. It doesn't look like I can. So I'll rewind here. So here's my initial value. I'm going to warp by, let's show velocity. And so here things are going to deform. Notice I'm going to guess that it's the rate and state is falling behind due to the direct effect. And it's going to catch up and then pass the static friction due to the weakening associated with the rate and state parameters. So I chose an A and B so that there would be weakening on the fault, and so that's why we had the direct effect of the coefficient of friction increasing above the reference coefficient of friction, and then when we kick in sort of as we develop toward the steady state behavior, we have a weakening, so our coefficient of friction is below 0.6, and so that's why it's getting ahead of the static friction. But it too goes to steady state sliding behavior. To solve, it's a highly nonlinear equation to actually figure out, and I think you have to solve it numerically to figure out what the steady state sliding velocity is. Oops. And we'll go forward in time. So we see the static friction going faster, the rate and state starts out slower, and it slowly overtakes the static friction. You'll see that right at the end of the fault, there's a little bit of left and right motion. That's because we can't constrain the X degree of freedom right on the fault as well as the relative displacement. So remember, our node set was everything except the fault because we can't overlap the Dirichlet boundary condition with the fault boundary condition. Any other questions? Any questions on using friction
to add a rupture in the quasi-static simulation?
So in our, we did the rate and state with stick slip behavior. So that was, we got the stick slip behavior with rate and state friction in the quasi-static simulation. And the slip weakening also, we had sticks, I believe that was step 13, has stick slip behavior with slip weakening friction. So is that?
Is he asking that, or is he asking whether you can include a dynamic rupture in the quasi-static simulation?
So you can't do propagating seismic waves in a quasi-static simulation because you don't have inertia.
Yeah, so I'm not sure.
Does that answer your question?
Oh. Okay. Okay.
About 10 to 15 minutes left. So we'd like to help you guys along. If there's any questions, we can do some more troubleshooting. I can try and get something not to converge and then show you what happens.